So today we're going to talk about normal tangential components as part of the dynamics course. So first, a definition. So there are two types of acceleration, normal and tangential. Normal acceleration is caused by the centripetal force, and it can be found by dividing the velocity squared over rho, where rho is the radius of curvature, and this is just the acceleration caused again by that centripetal force, which is always pointing inwards of the curve or the circle. The tangential acceleration is the rate of change of speed, which is the direction is tangent to the curve, and this is the same as any other rate of change of speed, any other acceleration. Tangential acceleration is simply dv over dt. The total acceleration is the normal and tangential acceleration combined. So this would be if you squared both and then added them and square rooted it. This is very similar to what we saw in rectangular components as well. Just a note, the radius of curvature rho can be found from the path equation if you're given a path equation, and it's simply 1 plus the first derivative of the path equation squared, all to the 3 over 2 exponent, and then divided by this absolute value of the second derivative of the path equation. So something that can be useful is that we can change our coordinate system from x and y coordinates to normal tangential coordinates. So looking at the system in terms of normal and tangential directions can make some curvilinear motion problems easier to solve, and then we can also convert back to rectangular components later if needed. So procedure for normal tangential components. First, we want to list out all of our variables, v, s, and a, so velocity, displacement, and acceleration. Then we should solve for tangential acceleration. We can use at equals dv over dt, or tangential acceleration times ds equals v dv. Then we can solve for normal acceleration. So we can use normal acceleration equals v squared over rho, and we might need to use that big radius equation to find for rho. Just a note though, steps 2 and 3 can be interchanged. Sometimes the question only asks for one type of acceleration. It's not like you need tangential acceleration in any way to find normal acceleration. So then to find the total acceleration, we can just use that equation squaring the normal acceleration and the tangential acceleration, then adding them, and then square rooting it. Then if we're asked, we can determine the direction. So we can use the simple trig identity arctan of the normal over the tangential accelerations to find the angle between the positive x-axis and the tangential direction vector, and then we can use this to convert to x and y coordinates. Remember that signs are important. Pay attention especially to the signs and directions of accelerations. So for an example, we have a particle traveling along a circular path of radius 400 meters. Its acceleration decreases at a constant rate, and it decreases by 10 meters over a distance, which would be the arc length, of the path of 400 meters. Again, that's the arc length. The speed of the particle at a point is 20 meters per second. So then we want to find the total acceleration of the particle at that point. There's also an extra example here, which I will post later in the description below. But we're going to work on this example first. So, if we go back here, so we can list out the variables given. So we know that rho equals 400 meters in this case. And then we know that the acceleration decreases by 10 meters per second over 400 meters. And then we know the speed of the particle at a particular point is 20 meters per second. So then the next step is to, we can solve for the tangential acceleration. It might be a bit easier. So what I'm going to do is I'm going to use this simple kinematic equation. We know that the acceleration is constant. That was mentioned in the problem. So I'm going to use this, and I'll explain in a minute. So we know the acceleration in terms of the displacement. So then we can find the acceleration, and we also know our velocity and the change in velocity as well. So to solve for AT, which is our tangential acceleration, it's simply v squared minus v naught squared over 2s minus s naught. And this is just equal to, so we know that the change in acceleration is negative 10. That just comes from up here. And we know that it is over 400 meters, which again comes from there. So then we can say that AT is negative 0.0125 meters per second squared. Okay, so we solved for AT, which is our tangential. Now we want to solve for normal. So this is simply v squared over rho. And we don't need to use that big equation for rho because it's already given. We know that v is 20 meters per second at that particular point. That's squared over the radius of 400 meters. And this is pretty simple, so it just comes out to 1 meter per second. So then we have our normal acceleration and our tangential acceleration. So for total acceleration, we're just going to add them here. So we know that A equals, AT squared plus AN squared. And that equals, leave that for now. That equals negative 0.0125 squared plus 1 squared. So then total acceleration is just 1.0000078, which is approximately equal to just 1 meter per second squared. So we can see that most of that acceleration actually comes from the normal. There isn't much tangential acceleration. That is all for today. Thank you again to Loom and to Google Keep, and of course to my professors. I hope this helps, and we'll see you next week.